Hi, my name is Hazim and today I'll be talking about order differential equations, its history, theories, and applications, along with a few examples. So, a differential equation describes the relationship between several variables and the rate of change in one variable. So, to begin with the history of ODE, since its introduction in the middle of 17th century, differential equations have been a significant area of law and practical mathematics. Leibniz and the Bernoulli brothers and others first developed differential equations in the 1680s, not long after Newton developed fluxual equation in the 1670s. So now, what's the ODE theory? The ODE theory states that the highest order derivative that a differential equation has is used to define the equation's order. The highest order derivative of a differential equation is defined as its degree, which is expressed as a power. If the function and all of its derivatives occur to the first power and the coefficient of each derivative is in the equation solely concerns the independent variable x, the equation is said to be linear. Various forms of ODE exist, such as linear, nonlinear, homogeneous, and non-homogeneous. So, a few applications of ODE in the field of biotechnology are: there are many biological laws and relationships which can be expressed mathematically as differential equations in molecular biology mathematics. Ordinary differential equations are formulated as expressions of the time evolution of concentrations of molecular species in vast majority of cell and molecular biology models. The equation describes a system with a large number of participating molecules of each other gives diffusion is high enough for spatial distribution of molecules to be homogeneous. So now let's move on to a few examples of ODE. Separable ODEs and non-separable ODEs. A separable ODE can be written in the following form: with us, and I've provided a solution where I have differentiated an ODE in terms of y and x by first separating them. So now let's move on to non-separable ODEs. If an ODE is non-separable, we might need to make it homogeneous in order to separate it. A homogeneous function is if in the nth term of every real lambda is symmetrical. For example, x squared plus y squared, we have the nth term of every lambda has power of 2. So we can call this a second degree ODE. So now to move on to linear and homogeneous and non-homogeneous linear ODEs. Sorry. A linear ODE, if a function is in the following form, then it's a linear ODE. An example of it has been given below, where a homogeneous linear ODE is when the Rx term, the 0 over here, is equal to 0. So then we can call it a homogeneous linear ODE. While a non-homogeneous linear ODE is said to be non-homogeneous when the Rx isn't equal to 0. For example, this is a homogeneous linear ODE since Rx equals to 0, while over here Rx, if it isn't equal to 0, for example 1, then we might need an so-called integrating factor, which we then use to multiply it with the entire equation. So lastly, homogeneous ODE and reduction of non-linear ODEs to linear ODE function. A homogeneous ODE is a function if every nth of every lambda is same or equal. For example, f bracket x comma y, x squared plus y squared, the solution has the degree to the power of 2. So we can identify this as a second degree homogeneous function, while the reduction of nonlinear ODE to linear ODEs can be expressed in the following manner. Over here we first formulate a function, for example u bracket x equals to this set of formula, where a should be given in the equation. For example, y to the power of 2 can be regarded as 1 minus 2 yx, and after we find this ux, we can use it as an integrating factor to multiply across the entire equation and then treat it as normal linear ODE and solve it using integrating factors and many other various methods. So that's all. I hope you understood what I meant, and thank you.